Welcome to Calculus. Today we will investigate function continuity, focusing on solving for a constant value to create a continuous piecewise function. We've taken a look at two examples. Let's take a look at three additional examples of making sure that piecewise functions, or for our last example, composite functions are continuous. Let's head over to our notes screen. Our first example for the second segment's here. So our task is to find the constant value of a so that each function is continuous on the entire real number line. Then we want to graph the continuous function by creating a table of coordinate points. And really, once we've solved for that a, the graph is going to demonstrate, hey, we have made that piecewise function continuous. So we're going to start off here by just checking out our two piecewise, really our one piecewise function with the two parts. So the one part is this rational x squared minus a squared over x minus a. So what I want to do is I'm going to bring that function over. And our strategy on the last two examples was to solve by putting the common x value in instead of x. Now, what we see here is that the common x value isn't a number. In fact, it's the very thing we're trying to solve for. The common x value is a. So what we'll do on this first one is we're not going to calculate f at x, we're going to calculate f at a. But before I do all that, I want to take a look at this first piece of the piecewise function, the x squared minus a squared over x minus a. So what we got to notice is that this numerator is the classic difference of two squares. And I think that if we can factor that, we can see some kind of cancellation. So I'm going to factor x squared minus a squared as x plus a. Do you remember how that would factor? What would go in the second binomial? Good, x minus a. Now that's all over x minus a. And at that point, I'll take a look and see, what do you notice between a comparison between the numerator and the denominator? What do you notice? Excellent. So I've got an identical factor, and remember, anything divided by itself attains the value of 1. And so what we see is that this f of x really boils down to x plus a. Now recall from our work with rational functions and functions with removable discontinuities, if you've got a cancellation like this, really what it says is that this is a hole in the graph. I know that because that x minus a is in the denominator, that it cannot equal 0. So there's an anti-equation for us. X minus a does not equal 0. And if I were to solve for x, I would add a over, and I would get this small anti-equation. See if you recognize it from the original piecewise function. X does not equal a. Well, and that's why we've got that in the piecewise function. If x equals a, it's going to be undefined. Luckily, though, we were able to reduce that down to just f of x equals x plus a. So we'll just hold on to that for a moment. The second function of this piecewise function is simply 3. So we're going to look at f of x equals 3. And at that point, what I want to do is I want to substitute in that common x value of a. So I'm going to erase, that's good, the x. And I'm going to substitute in a. And at that point, I can get rid of the x here. And so what we're seeing is that this first function is going to reduce to a plus a, or 2a. And because the second part of the piecewise function is a constant number, just 3, I don't do anything with it. What I got to note then is that if I'm matching them up, remember we got to have those x values and the y values the same. F of a is y, so I'm just going to say these guys are equal. 2a equals 3. And at that point, I'm ready to solve. So I'm going to divide both sides by 2 to solve for a. And that gives me a solution. A is 3 over 2, or 1.5. So I'm going to box that. That completes that first task. Our second task is to graph it to prove that that 1.5 as a makes this function continuous. So to do so, let's make our threefold table. And we make it 3 columns broad because I got x values, and then I also have 2 pieces in the piecewise function. So for my x's, I can kind of choose what I want. I'm going to go -2 through 2, but I also need to include what decimal value? What decimal value do I need to include? Excellent. So if x equals a here in the piecewise function, which is 1.5, I need to include 1.5. What's happening there at that common x value? And then 2. Okay, so let's sub in for this x squared minus a squared over x minus a. And what I want to do is I want to take this simplified version, which was just x plus a. That'll reduce my work quite a bit. So x plus 1.5. And keep in mind, I can use that simplified one because of that cancellation we saw with our x minus a's dropping out. So this is -2 plus 1.5, which is -0.5. This is -1 plus 1.5, which is positive 0.5. So definitely a slope of 1 here. 0 plus 1.5 equals 1.5. So it's going up by 1s. I can predict the next one's 2.5. And then 2 should be 3.5. What I have to note is that this 1.5 is undefined. And that again comes from this rule that we wrote that x cannot equal a. So what we'll do is we need to say, okay, what should the value be there? Well, we solved it already. This function is just 3, and it's only good when x equals 1.5. This is a different restriction on our domain. It's not half and half. It's really the whole x value number line with just one x value undefined for the first part of the piecewise function. Well, what fills in there is 3. And that's the only place where that second part has any sway. Well, let's graph that, see what we see. So at -2, we're at -0.5. At -1, we're at +0.5. At 0, we're at 1.5. 1, we're at 2.5. 1.5 was undefined, so I'm going to put kind of a red open circle at 1.5, 3. And then at 2, we're at 3.5, and then it would continue infinitely in both directions. So I'm going to graph that line. And remember, that was that one spot right at 1.5 had the value of 3. And if I find 1.5, that's here on the x, 3 is here, that really fits in just perfectly. And it's kind of like a puzzle. It's that last piece that we're inputting into place. Once we do so, that is a totally continuous linear function. Let's take a look at a piecewise function that involves base e exponentials, also base e logarithms. Excuse me. So the task is the same. I want to find the constant a. And that only occurs in one spot. It's up in the power. So e to the power of ax of this piecewise function so that the two of them create a continuous function. So remember how we start with these. We find the common x value. So looking at the piecewise function, what is the common x value? The one that they share as they join. Good, that's the 3. So what I want to do is I want to substitute in for this first function. What's f at 3? So that's going to be half e to the power of a times 3 plus 1. And then for the second function, again, anytime I see x, I'm going to substitute 3. That's the common x value. So it's natural log of 3 minus 2 plus 3 squared. So this one in red, we can simplify a little more. This becomes the natural log of 1 plus outside the argument 3 squared is 9. And at that point, we can simplify even further. And what I want to do is investigate this natural log of 1. What's the value of natural log of 1? So recall, natural log is equivalent. I'm going to just take this to the side because we got to do some work on that particular term. That's log base e of 1. And it equals some number. I'm not quite sure what it is, but it equals some number. So remember, the way that we simplify a natural logarithm is we go starting at the base, e to the power of that far side of the equal sign. So I'm going to write it here. E to some power that I don't know swings back around and equals the argument, equals 1. So really what I got to ask myself is, what should I raise base e to make it equal 1? What power makes any base equal 1? Excellent. If I raise any base to the power of 0, it will always equal 1. So e to the power of 0 equals 1. In fact, anything to the power of 0 equals 1. So this becomes 0. ln of 1 is 0. So this, like f at 3, really boils down to 0 plus 9 or just 9. That's nice. Well, with that simplified version, what I'm going to note now, just like we did in previous examples, is that those x values were equal. For our function, the piecewise function, to be continuous, we have to have our y values equal as well. So what I'm going to do is I'm going to take the right sides and set them equal. So we're going to set 1/2 e to the power of 3a. I just switched those around just for kind of convention's sake, equals 9. And that's nice because that's down to an equation with just a as our only variable, our only unknown. So I'm going to start solving that one. Let's subtract 1. That'll cancel on the left, and 9 minus 1 on the right will give us 8. So this is down to 1/2 e to the power of 3a equals 8. So then what would you do to simplify? We're trying to get a equals something. That's our goal. So yeah, good. Let's attack the 1/2. So I'm going to multiply it by 2. 2 times 1/2 is 1. Multiply the other side by 2. So that becomes e to the power of 3a equals 16. So at this point, I got to deal with the fact that the a is in the power, it's in the exponent, and I need to think, what's a strategy I can use to divest it from the power down to the main level? How can I elevator that power down to the main level? So recall from your study of logarithms that I can take the natural log, and that will do exactly that. By logarithm rules, you take the logarithm of a base to a power, and the power automatically moves to become a coefficient. So my next line, let me also apply natural log to the 16. So my next line is going to be 3a times natural log of e equals the natural log of 16. And we're on track at this point, because like that a is down on the main level. So we just have a few steps left. I do need to do something with natural log of e, kind of like how we dealt with natural log of 1 up above. So just let's convert it. A lot of times converting a logarithm to an exponential sheds some light on the situation. So it's log base e, that's equivalent to ln, remember, of e equals something. So the conversion is going to be base e to the power of some number equals e. So e to the power of some number equals e. So let's think exponential rules. If I've got a base, what power would I raise it to keep that same base only? What power would I raise a base to give me back the base identically? 1. So what this is, the natural log of e is in fact just 1. Well, that helps me out on this solution, because now at this point, what I've got is 3a times 1, or just 3a, equals natural log of 16. And then to solve, what would you divide by? Very good. Divide by 3. And that gives us a solution for a. I'm going to take it over here to the side. A equals the natural log of 16 divided by 3. And we might be tempted to try to simplify that further. That is going to definitely be an irrational number, a long decimal. So I'm just going to leave it as that. Now, the challenge is to graph this. So as I'm looking here, it appears that I've got all kinds of irrational numbers. So what I'm going to do is I'm going to create the threefold table, put the x values, and then let's use Desmos to help us evaluate some stuff. So x values, and let's go -2, -1, 0, 1, 2, 3. Let's go through 5. And what we're really looking for is that cutoff of 3. Those y values should be the same. So the first function is going to be 1/2 e to the power. Instead of a, I'm going to put natural log of 16 over 3. It's a lot to write, but that's what it is. X, and then plus 1. And then for our second function, we don't have to change anything there. It is what it is. Natural log of x minus 2 plus x squared. So let's head over to Desmos, and what we'll do is we'll create that table there, and then we'll recreate it here on our notes screen. So let's clear out this older function. And I'm going to type in those two that we had just written. So f of x equals 1/2 base e to the power of, parentheses, natural log of 16 over 3 x plus 1. And the way we're restricting this is that it is x is less than or equal to 3. I'm going to zoom out just to make sure. So yeah, we're getting a good restriction. Notice we got that point at 3,9 on that far right side of the logarithmic function, or the exponential function. Here's the logarithm. Now on Desmos, I need to call it differently. So g of x equals, and let's make sure we get that one correctly. One moment. So that's natural log x minus 2 plus x squared. Natural log of x minus 2 plus x squared. And we're going to truncate that one so that it's strictly greater than 3. And you can see from the Desmos graph that it's real seamless from that black curve transitioning into the kind of burnt orange curve. There's not any gap. It's seamless. But let's get some values so we can create that graph on our own. So for the first one, I'm going to record 1.08 at -2, 1.20 at -1, 1.5 at 0, 2.26 at 1, 4.17 at 2. And then I think I did that backwards. No, that actually is correct. It's defined also at 3. If I put that in the table as 9. So that's good for the left-hand curve. For the right-hand curve, we're going to start at 3. So you can see it's undefined all the way down. But let's just change it from 3 to 4 to 5. And then we're going to get rid of the rest. So we don't need those values. So at 3 it is undefined, but it has the assumed value of 9. At 4 it's 16.7, way off my graph, but we're going to record it anyway. And at 5 it's 26.0, really 10, rounding to the nearest hundredth. So let's recreate that on our notes screen. So I'm going to fill in the table with what we just saw from Desmos. 1.08, 1.20, 1.5, 2.26, 4.17, and 9. And then if I bump over to the other one, it has the assumed value of 9. I'm putting in parentheses because that second piece was strictly greater than. But if it had been equal to 3, it would have been 9. And then it really rises quickly, 16.7, 26.1. Let's graph it. So it looks like we got a horizontal asymptote at 1. So this at 2, it's just -2, it's just above 1, 1.08. -1's at 1.20. 0's at 1.5. 1 is at 2.26, so it's risen more. 2 is 4.17. And then 3 is off my graph at 9, and that's okay. I'm going to estimate that's about 9. And there's my left-hand function. Let's sketch that one in. So definitely a horizontal asymptote at 1. Left-hand side gets an arrow. Does the right-hand side get an arrow? Good. No, it's a firm point because that's a a restricted domain. Okay, the other one picks up, and I'm not going to even try to graph 4, 16. 16's up in the sky. It's enough to know that it's a very steep rise. And that does the trick. So even though we got a kind of a complicated a for this one, natural log of 16 divided by 3, it works. So we got to trust that process. Let's take a look at one final example, and this is a slightly different question that involves function composition. So we've got this h of x that is a composition of f of x and g of x. So we're saying that h of x is f of g of x. So remember, another way of writing this is f of g of x. And basically what that's telling us is I need to take the range of the g of x, which I can consider is this whole right side. That's a y value. And I need to replace that where the domain of f of x is. So that whole half x squared minus 3, it's going to go and live right here for x. And we know that order is because g is on the inside, and it's where the x of f of x was. So really we're just making a substitution. What's x in f of x is going to become all of g of x. So the way that I'm going to write h of x is as the structure of f, so 1 over 2 big parentheses. That's where x was. I've taken x out, plus 2. What I need to put where x was is the replacement g of x. And that is half x squared minus 3. So we got to compose the functions as a first step in order to define what is this h of x. Let's clean that up. So I'm going to distribute the 2 through the half x squared and through the negative 3. And that's going to give me 1 over 2 times half x squared is 1x squared, or x squared. 2 times negative 3 is negative 6 plus 2. And that's going to reduce down to 1 over x squared minus 4. So we don't have instructions to graph this one. I do want to make a sketch though, because that's going to help me write these intervals over which h of x is continuous. So it's a rational function. I'm going to factor the denominator. So it's 1 over x plus 2 times x minus 2. And looks like that's a rational function. It's got a horizontal asymptote of y equals 0. And again, I know that because on the original, the high power on x was in the denominator. And then I've got 2 vertical asymptotes from these 2 linear factors in the denominator. So I'll set them equal to 0. Really, I'm saying that they cannot equal 0. That's the implication. Why cannot they equal 0? Because I can't divide by 0. Good. So I'm going to solve those anti-equations, subtract 2 on the left one. So x cannot equal negative 2. And then on the other one, x cannot equal positive 2. I should put a 0 there. So to help me see where this function is continuous, I'm going to sketch this graph. So over here on the left, I'm going to place a horizontal asymptote right on the x-axis. So I'm going to overlay a dashed red line on the x-axis. That's my y equals 0 horizontal asymptote. And then I've got two vertical ones. There's this one at x equals -2. There's this one at x equals +2. And I believe my graph fits in those kind of three intervals. So my feeling is if I'm writing where f of x, I'm sorry, where h of x is continuous, it's going to be based on those three intervals. Now, what I'd like to do, I could create a table with this, but I'm going to select the calculator tool, and I'm just going to take this function, the simplified version of h of x, 1 over x squared minus 4, and I just want to look on Desmos and just make sure that there's actually pieces of the graph in each of those three partitions of the x-axis. So I'm just clearing out the work from our previous question. So let's type in f of x. Let's keep it h of x equals 1 divided by x squared minus 4. And that looks really, really exactly right. So if I check my vertical asymptotes of x equals -2, there's that blue vertical one on the left, and x equals +2. And then the horizontal asymptote of y equals 0. And those three asymptotes really do follow the shape of the graph. So I don't really need a table because my goal is just to say, where's it continuous? It's continuous on the left of -2, it's continuous in between -2 and 2, and it's continuous from 2 and beyond. So we just need to write that. Just to catch that function, let's place it in here. So this was the graph. So on the left, it's there in quadrant 2. In between, it's in quadrants 3 and 4. And then on the right, it's in quadrant 1. So the intervals over which h of x is continuous, there's three intervals. So the one interval here is going to be from -infinity. So I'm putting it in interval notation up to what x value? -2. That's that left branch up in quadrant 2. In between here, it's continuous from -2 to +2. That's that upside down u. And then the right-hand branch is continuous from -2 out into the great beyond, into infinity. And that I would box because that's really the answer. That's the interval over which this function is continuous. Thank you for joining for these 3 examples to finish out our 5 examples total of creating continuous functions from piecewise functions, and then also looking at this composite function. Thank you for joining for this video. We will see you soon.